we can start with the quiz. So, the stand was what, 20 grams? What is the weight of that stand or mass? 20 grams. And this one magnet? 60. Okay. This one? 60. Fine. 20 plus 60 plus 60. 140. And the answer is 5. What would be the final reading? Yes. What did you write? I didn't write it. You didn't write it. What will be the final reading? You have seen the stand is 20 grams. Each magnet is 60 gram. And now they are put in the repulsive mode, so that one magnet is hanging in air. So now what will be the reading here? 140, right? Huh? 60 plus 20, 80. Yes? Oh, there is two sides, so 80 and 140. 100.
60 plus 40 plus 60 plus 20 plus 20.
60 plus 20 plus 20. 100. Yes? What do you think?
So when we put some weights on the pan,
Yeah?
so that pan, when we keep it on the pan, it exerts an impulse on the
Right.
pan which gives the weight of the pan.
Okay.
So when we put them separately and when we put them together, the weight won't be equal. It will be slightly, when we put them together, it will be slightly less than when we put them all separately.
Yeah, in this case, your magnet, the other magnet is just hanging because of the repulsion from the lower magnet. And the magnets are 60 grams, 60 gram, and the stand is 20 grams. So, what do you think will be the reading shown? Yeah.
It will be less than 140.
More than? Let's put the limits. Less than 140 and more than? What do you think? 80. Okay, now there are some divisions. 140.
No, I would actually.
Yeah, 140. I understand that. This is all, you all go for 80? 80 you said, right? Okay. Now this is going to be 140 grams. Okay. कुछ है क्या डंडा वंडा? यहाँ एक डंडा होता है. ये रहा. Okay. Because what happens is, although it is hanging in air, but it is also repelling this magnet, and therefore pushing it down. All right, and the force by which it is pushing it down, that repulsion force, is same as the repulsion force by this magnet on that magnet, Newton's third law. And since this is in equilibrium, it has to be 60 grams weight. So it is pushing it down by 60 grams weight, so that is added, right. So total is 140 grams. Yeah, Ranjit, next. Huh? What is that? Okay. It was there yesterday? All right. This one? That's what he started with. All right. So you have a spring balance, you have a weight, and this is now how much of the stop karna? Okay, it's there. So 500, 600, 620. Let's say 620. The dial on the panel reads the mass and the object panel in the grams. Okay, so it is 620 grams. Find the mass. What? What is this object? And what this object is? Can you identify what this object is? It's a what, battery or some kind of a can? What it is? Capacitor? Ranjit, what it is? Capacitor. Okay. The red pointer of the spring balance, okay, here. So this is 1.2, 1.4 newtons. Remember, this is 1.4 newtons. How many grams? 140 grams. Okay. So this is 140 grams. And that 140 grams becomes 0.2, 0.3. 30? No, even less. Even less. 0.2. 20. 0.2 is 20, right? Okay. All right, 0.24. So 24 grams. All right. Now, so what will be the reading of that balance? 620 minus 620 minus 24. What is the reading of the pan balance there? It was 620 to start with, and now you have put this thing, and that was 140. 140 gram was the weight of this object, and now it is reading only 24 grams. So what is the reading of that pan balance? Dial reading. It will increase or it will decrease? The pan balance reading will increase or decrease? It will increase. It will remain same. It will increase. Any taker for decrease? You said it is minus 24.
No, I said initial weight of the thing plus the weight of the object minus 24.
Okay, okay. So what is being done here? If you consider this beaker plus water as your system, this object is pushing it down, right? Water is pushing the object up. When you are dipping this solid object in water, water is pushing the object up. So object is pushing the water down. So if you look for this water plus beaker system, your forces will be initial that 620 grams, I am talking in grams into G of course. So 620 grams is earth is pulling, then this is pushing it down by how much? 140 minus 24, right? That is the Archimedes principle. It was 140, and now that spring balance is 24. So the remaining is coming from water, correct? Remaining is coming from water. So minus 24, whatever, 140 minus 20, 116, right? 116. So this is pushing water 116, earth is pulling 620. So this is the downward force, 620 plus 116, 736. So, the downward force is the 736, the upward force has to be 736. So, this base of that pan balance is pushing it up. Base of the balance is pushing this base of the beaker up by 736 grams, and therefore, the reading shown will be 736 grams. Okay? Yes. Colored water bottle 1, bottle 2. So, you are opening it, all right, atmospheric pressure. Pressure of air, okay, pause kar this. Okay. Pressure of air in bottle 1 is less than atmospheric pressure, more than atmospheric pressure, or equal to atmospheric pressure. Wait. So, you had a bottle with colored water in it connected to another bottle, right, no water, and both the caps were initially, at least you had seen that they were closed, but that empty bottle, that cap is now open, okay, and the colored water cap is closed. No water is going from that side to this side. Now, the question is, in that water bottle in which water is there, the pressure of air above the water, is it less than atmospheric pressure, more than atmospheric pressure, or equal to atmospheric pressure? Less than. Huh? Argue for it, why it should be less than? You understand it should be less than atmospheric pressure? Why? पीछे वाला बॉटल दिखा देना जहां कैप खुला हुआ है. पीछे पीछे पीछे. Why people think that, yeah, this is the situation. Why the pressure of air in this bottle here is less than atmospheric pressure, if it is? Right. So, here you have it is open to atmosphere. So, here you have atmospheric pressure, and therefore, here you have atmospheric pressure, and then you are going up in water. So, when you are going up, the pressure is decreasing. So, it is atmospheric pressure here and then less than atmospheric pressure here. Chalo. Next karo or ho gaya, next karo. There are other questions. I wanted to skip. I know there are 3 parts. It's okay. Okay, pause. The pressure of air in bottle 2 is, I have already given the answer. Chalo, aage badho. That's why I was skipping. Okay. Now, if the cap of the bottle 1 is opened, what kind of water flow do you expect? No water will flow. Some water will flow from 1 to 2 and water will be equally divided naturally. Chalo. So, one object, when you put in water, it tilts, and another object floats vertically. So, guess the difference in construction and why this difference gives this phenomena. किधर से? Yeah, up there. What do you guess? What is the difference between these two objects? One is hollow, other is solid. One cylinder is hollow, other cylinder is solid. Do this experiment somewhere in the after classes are over. Put a solid cylinder in water. What do you think? Will it float vertically? A solid cylinder. If you put a solid cylinder, will it float vertically? No. Put a hollow cylinder. Will it float vertically? No. Both of them will tilt. Yes. Okay. The corks which are attached, one cork is solid, another is hollow. Guess what is the difference between these two? Meta centers. Yeah, but construction. How did we construct? What did we do to these two things so that the meta center and other things are the way they are there? How did I construct it? Now, who has constructed it? आपने construct किया है? अमित आपने हाँ आप बता दीजिए. What is the difference between these two? How did you construct?
One pipe is hollow and put it one base or pipe, that one, and this one is filled by some sand
Up to some height.
up to some height, and I will check that time if it is floating or not.
Okay. So, they are similar pipes and similar these stoppers base, and then one is okay completely empty. In other you keep putting some sand. Right. If you put very small amount of sand or weight, then it will again tilt, but if you put proper amount of weight there at the bottom, then it will float vertically. Now, this is a very interesting to analyze this, that meta center and other things are there, but to really analyze that what governs this tilting, if there is some object and you put it there and it tilts. So, depending on the shape, the center of mass and what it is placed, if you do a proper analysis, which direction the torque will be and up to what angle it should tilt, it is a very good mathematics. It is a very good mathematics. Sometimes if I get time, I will discuss that. Yeah. Yeah. Wavelength. Okay. Of course, camera also alters the colors, because camera is also an optical instrument. So, what is actually on the table and what comes out in the camera, the colors are sometimes not the same, but this is red. All right. So, we read this formula, a wavelength changes when it goes, the frequency does not change, the speed changes and hence the wavelength changes, right, and the wavelength changes by original wavelength divided by refractive index. So, if I do that, it should be green, but still red. All right. If I look from inside, what happens? Of course, laser should not go directly into the eye, but suppose I want to punish someone and I dip that person in the water and look at the laser. So, what kind of color that person will see? Green. Frequency remains the same, wavelength changes, color also depends on frequency or depends on frequency? Does not depend on wavelength. Frequency does not change, that is fine, wavelength changes. Now the question is, if my eyes are right in this water and I am receiving that thing, whether I see green or whether I see red. Frequency is same, wavelength is different. Huh?
You can have a vote.
I can have both.
A vote.
Vote, okay, you can, okay. No, what will happen, there is a, nowadays there is an option, what, nota or something. So, क्या बोलते हैं? None of the above, nota, right. Not in the, not above. वो बैलेट पेपर में क्या नया जुड़ा है इस बार? None of the above. अच्छा, उसमें भी above ही है, okay. So I am sure many of the people will go for that. How many of you say green? When you are sitting inside the water. When the eyes is inside the water, green. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, around 20, half the audience. And how many of you say it will be red when you are seeing from inside, your eyes are inside water? 1, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 10 have gone for that nota. And my answer would be, you will see,
So, this light looks red because there is a difference in the time scale of two things there between the path that the light travels by the speed of light and the persistence of human eye. So, since there is a difference in the time scale, the eye can perceive the color to be once red and then green from outside.
from outside, what do you perceive?
So, there are two time scales which are considered here.
There are two time scales involved.
So, one time scale is the length that the light travels between the portion it travels from air to water, and that portion is the time that it takes, that length divided by the speed of light.
This one, this
yeah,
way.
Yeah, that length divided by the speed of light,
Okay.
and the time of persistence of human eye. So, since this is very small because of the great magnitude of speed of light, so the eye can perceive the difference between the two colors from outside.
But, okay, fine. And what happens with the eye here?
If we are inside the water, then
I'm not taking correct. Suppose I'm just, from outside I have just gone inside.
if we are viewing the light from inside the water, then it appears green. But if we are look it from outside, that's why it's appearing red inside the water because of the.
My take will be, what you perceive depends on what happens on your retina. Correct? Whatever is happening outside, I am not concerned. What happens when that light falls on the rods and cones of my retina, only that will create voltage signals. Only those voltage signals go to the brain, and then the analysis is done and I perceive certain color. Okay. Now, it may come from air to my eye, it may come from liquid to my eye, right. Once it is in my eye, it is in my eye, and there is a liquid, what is called aqueous, vitreous, something. So, now before falling on retina, it is on that, in that liquid. Outside it, I have, how can that affect me? Okay. So, whether it is coming from air to my eyes or it is coming from water to my eyes, once it is in my eyes, the frequency remains the same, remember. All right. So, the whatever on the retina, whatever happens on the retina. If you talk of wavelength, the wavelength is wavelength in air divided by refractive index of that aqueous vitreous or what is. So, that lambda by that n, not the n which the light has gone through when it was outside my eye, right. Once it is in my eye, at the surface At the surface, when it is changing, when it is going from one medium to other medium, something happens on the surface. But once it is inside the other medium, it loses all memory of the first one. Now it has started into that medium and it just sees that medium. Okay. So, that relative refractive index will determine that angle of deviation and those things. But once it is falling on my retina, whatever is wavelength, frequency, photons, photon energy, photon momentum, whatever, that is that's same, independent of whether it has come from air or it has come from water. Okay? Chalo, next.
So your answer will be
Red, yes, red. Okay, so you have a pencil. All right. Now you put water. Now seeing from above. This person is Mr. Anurag Pandey. This is how you see from above. And now seeing from side, still not through water, the light is still coming through air. Viewing at an angle, the pencil appears much more sharply bent. Qualitative, do not draw ray diagrams. Qualitatively, can you tell why this difference? Here is that pencil. Now I am seeing from above and then I am seeing from side. Yeah.
Sir, the angle of deviation of the ray depends on the angle of incidence, and when it is viewed from a side, then the angle of incidence is greater than when you see from the upper side. So the deviation will be greater and the refraction will be greater in the latter case. So it appears to be more sharply bent when you see from the side.
Okay. Good. Fine. And then once you draw the ray diagrams, it will be clearer. The other phenomena is that the difference in left and right is very sharply recognized by eyes, but difference between the depth there is not that sensitive, right. Left and right is very easy to recognize, but forward and backward is more difficult. You see all these stars in the night and planets, they are at very different distances, but we see them all, it looks like they are in same at same distance. You do not say that okay, this particular star is far behind and this particular star is closer to me. Okay. This is an extreme example, of course, we are talking of light years. It is an extreme example, of course, but the fact remains that left right is easy to distinguish than backward forward. So, that is it. When I am seeing from above, I am trying to see the difference backward forward. When I am seeing from side, I am trying to see the difference left and right. Okay. Chalo. Okay, so why the separation between magnets 2 and 3 is more then the separation between 1 and 2. Try, you try.
Because when first and second magnets are put into the sand, the distance remains the same as it is in second and third. But when the third magnet is put on the sand, it presses it downward. The second magnet, it presses downward, and that's why the distance decreases. And the second and third distance remain the same on the first and second.
Okay, so what he is saying is, if only two magnets are there, then the separation is same as the separation that you are seeing here, right. But when three are there, this separation is same as if there are only two magnets, and but this separation is decreased because this magnet has pushed this down. Okay. Okay, good. You try.
The magnet 3 is repelled in the same direction by 1 and 2. The magnet 2 is being repelled in opposite directions. By 1 it is being repelled in upward direction, and by 3rd it is being repelled in downward direction.
Okay. Okay, simple, right. 3 is repelling 2, so it is pushing it down. Gravity is there. So, this magnet has to provide upward force which balances both these combined. So, the repulsion from here is downwards, and the gravity is also downwards. So, the downward force is more, so upward force should also be more, and for that the separation should decrease. So, that is why this separation is decreased. What happens about this? It is being repelled by this. Is it being repelled by 1 also? Being attracted, huh? So, for this also, if it is being attracted, so for this also you have a downward force, attraction by this, repulsion by this, and the gravity. These three are to balance. So, what do you think? This separation it's same as if only two magnets are kept, or it's more than that, or it's less than that? Less than? Less than. Okay. Now, the second, is there any more question in this? I have a question. Okay, pause. Now, tell me, what do you think? What should be the relation between force between two magnets and the separation? The force, just suppose there are only two magnets, or does not matter, the force between these two, common magnitude of forces by these magnets on each other, F, and this separation, R. So, what do you think? F will be like 1 by R or 1 by R square? 1 by R square. 1 by R square? Huh? 1 by R square? 1 by R square? Okay, unanimous. 1 by R square? 1 by R square? Anyone differing from this answer? And you will have to explain why do you differ. I will differ.
Can you give us 30 seconds?
Yeah, right, think on it. I am giving you the answer. It will not go as 1 by R square. Okay, now you explain this answer.
Because the force of gravity is also involved in
No, I am talking of magnetic force. Magnetic force depends on the separation between these two, right. The gravity will not change the force law. If you are holding the two at 1 centimeter, there is certain force. So, I am holding, that does not matter. If it is a 1 centimeter, this much is the force. If it is 2 centimeter, this much is the force.
Yes, 1 by r.
1 by r. Why?
Is it correct? Because then I think I can manufacture it.
Okay. Manufacture some argument for it.
My intuitive first thought was it has something to do with magnetic behavior of a coil is usually 1 by r first turns from 1 by r.
Okay. Okay, good, very good. If you have a circular current and you look at the center magnetic field at the center, it goes as 1 by r. You write mu naught I by 2 r, or even if you have a straight current and you look for the magnetic field, you write mu naught I by 2 pi r. So, it is 1 by r, all right, and a magnet is equivalent to a current loop. Okay. So, that is his guess that perhaps it should go as 1 by r.
But at any point on the axis of the loop, it does not vary as 1 by r square.
At any point on the axis of the loop, it does not vary as 1 by, and does not vary as 1 by r as well, right. That 2 pi by 2 mu naught I by 2 r tells me, okay, it's stable there, it's stable there, equilibrium. So, that mu naught I by 2 r, that r is the radius of the circle. So, if you are changing loops, bigger loop, bigger loop, bigger loop, and then looking at the magnetic field at the same point, then yes, it goes as 1 by r square, 1 by r, it goes as 1 by r. But here what we are looking at, the magnet is there and then we are changing the separation. So, as he says, you should think in terms of, you have a coil and you are going away from the coil and then see how it changes with that distance. Okay. And for that you have some complicated formula, A 3 by 2, right. Okay. If you have circular current and on the axis at a distance r. So, if the radius is say a, then it is a square plus that r square to the power 3 by 2 in denominator. Okay. That is how it will depend on r, not as 1 by r, not as 1 by r square. At large distances, what will this give? 1 by r? R cube, it will give 1 by r cube, right. It is a square plus x square power 3 by 2. So, at large distances, when radius is small, you neglect it, square and 3 by 2 will be cube. Okay. So, if you have a magnet and if you are at a large distance, you expect the magnetic field to go as 1 by r cube. Okay. And if you are close to the center, if you are close to the center, if radius is large, 1 by r. Okay, let me see. You have to work out. You have to work out. Let me see. So, you have 1 by this is the radius, and say this is the distance to the power 3 by 2. And now what I am saying is r is small. So, take that capital R cube outside, and it is 1 plus r square by capital R square to the power minus 3 by 2. Is that okay? I am taking this r square common. So, it is 1 here plus r square to the power 3 by 2, and that I can write as to the power minus 3 by 2. And since this is small as compared to 1, I can use the first expansion term in binomial expansion, and then it will be 1 by r cube 1 plus 1 minus 3 by 2 r square by capital R square. So, apart from that constant a DC shift is there, this constant 1 by r cube, and after that it is r square dependent, not 1 by r square dependence. But remember that constant term is there. So, do not think that it goes as r square, that means if I increase the distance by a factor of 2, the field will increase by a factor of 4. No, because that big term is there, and from that you are subtracting something. What you are subtracting, that depends, that goes as r square in the numerator. So, that is how the dependence will be there. It will be instructive to really make a plot, see what is that, where is the minimum, where is the maximum, and all those things, how that field changes. Yes. Okay. Okay, okay, very good. Amit, Ranjit, this is for you. Design. These 3 magnets are similar, all right. So, if we take magnets of different strengths, how does how do these 2 distances, can we manipulate that and make them equal? All right, good, thank you. So, it is not very simple. It is not very not simple to say whether it will be 1 by r or 1 by r square or 1 by r cube, number 1. Number 2, that is only the magnetic field. What we are talking of force between the 2 magnets. Suppose you have magnetic field at the second magnet, right. Suppose you have some magnetic field here. Suppose there is some magnetic field, say B, at this position. What is force on it? What is force on this? I give you the magnetic moment. What do I give? For a magnet, what is the characteristic parameter? Magnetic moment. I give you the magnetic moment is m, placed in a magnetic field, say capital B or B naught. And field is also vertical, and the magnetic moment is also vertical. What do you think will be the force on this magnet because of this magnetic field? mb sin theta is one answer. I am now talking of a single magnet. There is a magnet placed in magnetic field. The magnet has got a magnetic moment capital M, all right, and then there is a magnetic field B there. So, the question is, what will be the force experienced by this magnet due to the magnetic field? The field direction is same as the magnetic moment direction. M cross B. So, it is 0 in this condition. If the magnetic field is at 90 degrees, it will be M into B. That is another answer. Field is uniform. Yeah, go ahead. Then the force will be 0. That is third answer. Okay. This row, M cross B. all right. Yeah, this row m into b, okay. This side 0, okay, good. 0, 0, m cross b.
So there's a field around, so it's because of a magnet, because of a magnet. So if we assume that there are two magnets and they are kept like this, and so how is it that there is an angle? They should attract equally by zero.
Okay, all right. Why should depend on angle? Suppose I have two magnets, one magnet is like this, another magnet is like this. T, T. Will it attract, will it repel? You have north pole, south pole, let us say this is north pole, that is south pole. So I am putting it this way, what will it do? Huh. It will start rotating. No, oh, okay, that is a supplementary question. My original question is, you have a magnet with a magnetic moment m, and then there is a uniform magnetic field. So how much is the force, m into b or m into b into some sin theta or 0? It is 0. Okay, it is 0. If you have a closed loop, your magnet is equivalent to a closed loop circle, current, circular current or current, closed loop current, right. If your magnetic moment is say in vertical direction, it is equivalent to a current in the horizontal plane. Now, if you have a uniform magnetic field or a magnetic field, the force is, can you see this side, you people? The force is dF is I dl cross B, right. And therefore, the total force on this loop will be, current will be same in the loop. You will not have 1 ampere here and suddenly 1.5 ampere on the other part of the loop. So, I you can take outside the integration, and if this is uniform, then that can also be taken outside and it is like this. Okay. And if you add this dl vector, dl vector, dl vector, dl vector, and it is a closed loop, what it will be? It will be 0. You have dl vector, then dl vector, then dl vector, then dl vector, then dl vector, it is closed loop. So, if you sum all these dl, that will be 0. So, a uniform magnetic field does not exert any force on the magnet. We will kal kiya nahi tha na ye? We will have some demonstration someday that a uniform magnetic field does not exert any force on a magnet. You have to have a non-uniform field, only then the force will be there, right. So, even if you have a magnetic field, you know that the magnet, suppose you say that okay, the magnetic field of this magnet is going as 1 by r cube, does not mean that the force is going as 1 by r cube, right. It is the non-uniformity of magnetic field which decides the force, not the magnetic field itself. It is not B that is deciding the force, it is dB dz that is deciding the force. How B is changing with Z. So, if the field is like 1 by r cube, all right. So, how will this dB dr, if I change r or if you call it Z direction, if the field is like 1 by Z cube, then how that dB dz will go? dB dz, B is going as 1 by Z cube, some constant divided by Z cube, dB dz 1 by Z power 4. So, the non-uniformity is defined by 1 by r to the power 4, and that decides the force. Okay. So, if the separation is large enough, magnets are tiny and the separation is large as compared to the thickness of that magnet, it will go as 1 by r to the power 4. Of course, here the distances are not very large. So, there will be a complicated expression, not like 1 by r square, 1 by r cube, etc. Right. As you increase the distance, gradually it will follow that 1 by r, it will go closer to 1 by r to the power 4. Okay. Chalo Ranjit, next. पावर पॉइंट वाले क्विज भी थे क्या या केवल यही थे? वो भी है. ओके. It falls pretty fast and this goes slow. What are the materials used in inclined plane 1 and 2? Diamagnetic. 1 is diamagnetic and 2 is paramagnetic. Okay. So, what does diamagnetic do and what does paramagnetic do? All right, that was one guess. Any other guess? What is the difference between these two materials, plane 1 and plane 2? It's the same incline and friction coefficient is same. We have put paper, same kind of paper, but the speeds are very different. What is non-magnetic? You are talking of diamagnetic, you are talking of paramagnetic. What is non-magnetic then? Non-metal. One is non-metal, another is metal. I mean, is a metal non-metal difference or paramagnetic diamagnetic difference? Paramagnetic diamagnetic. Okay. Is the same magnet? Is the same magnet that we are putting here?
The negative power of the magnet,
Okay.
it can be weak. It cannot exceed the gravity.
But they are at the same incline, so the gravity effect is same and it's the same magnet.
The plane 1 is non-magnetic material.
The plane 1 is non-magnetic material. Okay.
The plane 2 can be ferromagnetic material.
Can be ferromagnetic material. It's weak. Okay. All right. Let me tell and then you say whether I understood you or not. Plane 2 is a ferromagnetic material. It attracts the magnet, but it's not strong enough to keep it there. Right. So it attracts, but the gravity is there. So although it is attracting, but it doesn't stuck there, and it falls, but slowly because of that attraction. Okay. But if it is weak, if it is very weak, no, suppose it is ferromagnetic, but the magnet is a weak magnet. So the attraction force is small as compared to the gravitational force mg sin theta. The component of the gravitational force is mg sin theta, and then of course attraction, but another thing, attraction will be perpendicular to the plane. And gravity is parallel to the plane. So how this perpendicular force can affect this gravity? Frictional force. Okay, okay, fine. So friction will increase, right? If the normal force increases because of this attraction, the frictional force will increase, and that can slow down. You are not right. You are not. So yeah, possibilities. Now you think of possibilities. So this is one possibility. The kind of thing what is there that I will tell, but this is a possibility perhaps that you take a ferromagnetic material, a very weak magnet, so that the magnetic attraction is not strong enough and the gravity is able to pull it down, but of course, it slows down and so on. This is a possibility. Okay. What is your guess? What can be the difference between plane 1 and plane 2? Magnetic properties are different, fine. First one must be a diamagnet. Paramagnet or ferromagnet. So, essentially the same argument, okay. Okay, different argument.
Plane 2 is a conductor material, plane 1 is not a conductor, the magnet is inducing any currents in the second plane, and that is plane.
There is another argument, right, another possible scenario, that your plane 2 is a metallic one, non-ferromagnetic. This is not ferromagnetic, we are not going into the, we are not using the magnetic properties, the metallic properties that we are using. So, it is a metal, and as this magnet travels, there are some currents induced in this metal. You know that? If the magnet travels, if it slides, there will be some currents induced in the in this plane, metallic plane. If it is metallic, if it is conductor, then some currents will be induced, and those currents will create their own magnetic field, which will pull this magnet up. This is essentially Lenz's law. The currents are induced because the magnet is going down. So, the currents will pull this magnet up, the direction of current will be such that it pulls the magnet up. And in the other case, plane 1, it is a non-metallic material. So, although induced EMF is there, induced current is not there, because you do not have free electrons to support that current, and therefore, there is no magnetic field which can pull this up, and it goes fast under gravity. Actually, the one which is here on the board is like this. This one is aluminum, and this one is mica sheet, that board on which we put the switches and sockets. So, that board here. So, this is all what you call non-magnetic. By non-magnetic, I mean either diamagnetic or paramagnetic. Both the effects are very small, very tiny. Okay. The magnetic attraction or repulsion by paramagnetic, diamagnetic materials is very, very small, 1 part in 10 to the power 5, 6. That susceptibility table, if you see, for paramagnetic material or diamagnetic material, it will be like 10 power minus 6 or so, 1 plus minus 10 to the power minus 6. So, it is that weak, that is why commonly we call them non-magnetic material, paramagnetic plus diamagnetic, both this group is called non-magnetic, and magnetic means ferromagnetic or anti-ferromagnetic or ferrimagnetic. Okay. So, that is the eddy current business. Yeah. Okay. Now, you have some PowerPoint questions. Okay. How long does it take for the energy to reach the surface of the sun? Okay. See, radius of the sun is this much, and energy is produced at the core only, in the core only, at the center, near the center. So, from that center to the surface of the sun, from the surface of the sun, how much time does it take to reach earth? 8 minutes, few seconds, right, something like 500 seconds or so total. Now, the question is, from the center of the sun to the surface of the sun, and radius is this much, how much time this energy which is produced at the core reaches, how much time does it take to reach the surface? How much it will be, how many seconds roughly? 2.3 seconds. Huh? How much time it should take from the center to the, it is this radius divided by the speed of light. Speed of light, how much is speed of light? How many kilometers per second? 3 into 10 to the power 5. So if you divide this by 3 into 10 to the power 5, how much you will get? 2.3 seconds. Yes, what you are saying?
Longer, considerably longer, because the sun, the material of the sun itself has its own refractive index that is particularly high and absorbs the image.
Guess 2.3 seconds if it is speed of light, vacuum speed. Guess how much it should be? 3 from 2.3 seconds. What is your guess? How much?
It's not entirely a blind guess because I sort of remember reading this somewhere, but
Yeah.
several
Several
in
in years.
long, large.
Okay. It is something like 100,000 years. Okay, it's like 100,000 years of that order. Light takes to go from center of the sun to the surface of the sun. It's not refractive index of that material, in fact. It's not refractive index of that material. In fact, it is difficult to define refractive index there. It's a highly dense plasma, right. So, those plasma properties, how plasma interacts with electromagnetic waves, they come in. So, in a popular language, what I can say is, when this energy is produced during nuclear fusion, they are in the form of gamma rays, not visible light. If you look at that reaction, hydrogen plus hydrogen going to helium, you have 4 steps, right? P plus P makes deuteron and so on. So, the energies which are there, they are all in mega electron volts. If two protons make a, what will these 2 protons make? Yeah, deuterium, deuteron. Deuteron is 1 proton and 1 neutron. You know that? Heavy hydrogen, heavy water, that hydrogen is 1 proton plus 1 neutron and nucleus, and then of course you have electrons. In the core of the sun you do not have that bonding, electron bonding. So, it is all bare nucleus. So, 2 protons combine to make a deuteron. Why? Why not a diproton? P plus P equal to P2, P and then subscript 2, H plus H is H2. So, P plus P is P2, diprotons. Why do they make deuteron? 1 proton, 1 neutron. You remember this, in school days you must have seen this reaction. Pi mesons. What is pi meson? What happens here in this reaction? They are produced. The protons are converted into neutrons, but why? But why? Proton is proton. It should remain proton. The other proton is not converted. There are 2 protons. They combine. One of the proton is converted. Other proton remains proton. Then you have deuteron. You do not have dineutrons. Two protons. There will be repulsion, Coulomb repulsion. No stability of nucleus. Okay. Okay. What about the dineutron? You do not have Coulomb repulsion there. There are no electrons involved. The electrons are far away. At those temperatures of 10 to the power 7 Kelvin, neutrons cannot remain attached to the nucleus, electrons cannot remain attached to the nucleus. So, electrons are nowhere in picture. Okay, electrons are nowhere in picture.
So if there will be that influence, then there will be no repulsion as well as no attraction.
Why? Neutron and neutron attract. No. The force is very. That is okay. Then how this helium nucleus is stable? In helium nucleus, you have 2 protons and 2 neutrons, right? So there is a repulsion. 2 protons are there. So there is a repulsion. So how this helium nucleus is stable? Alpha particle. How alpha particle is stable? What binds them? There must be a strong attractive force, stronger than this Coulomb repulsion. Where does it come from? Nuclear force. So, the neutron and neutron, they also operate through nuclear forces. Proton and neutron also operate through nuclear forces. Proton also operate through nuclear forces. Nuclear force. What is the electric force? What is gravitational force? Yeah. So, this is force between nucleons. Proton and neutron, there is a combined word for them, nucleon. Okay. So, the electric forces are because of electrons, the nuclear forces are because of nucleons. If you have 2 nucleons, you will have nuclear force. Yeah, attractive to up to some separation. If the separation is even less than that, it becomes repulsive. So, this helium alpha particle, helium nucleus alpha particle, it's not that because of the attractive force it will shrink into 10 to the power minus 51 meters. It will not. It will stay at some femtometers, 1-2 femtometers, because if you compress it further, bring it closer, the nuclear force becomes repulsive. So, this nucleus has a size, right. Nuclei, in fact, all nuclei, if you see in the periodic table, they will have size some 1 femtometer to 6-7 femtometers, 10 to the power minus 15 meters, that is the size. Okay. So, nuclear force becomes repulsive if the separation between the nucleons is very small, but at something femtometers type distances, 10 to the power minus 15 meter type distances, it is a very strong attractive force. Anyway, our question was different. So, when these 2 protons combine, they fuse to make a deuteron, energy is released. And then the deuteron combines with one more proton to make that helium 3 particle, and that combines with something else, and finally you have a helium alpha particle. Now, whatever energy released as photons, the energies are in mega electron volts. And what is the energy of a visible light photon? Range, order. Different colors will have different energies, but what is the order? Red light, how many electron volts or kilo electron volts or mega electron volts or milli electron volts will be the photon energy? Around? Okay, let us connect. You have, of hydrogen atom you must have done. What is the ground state energy of hydrogen atom? 13 minus 13.6 eV. Next, divide by 4. Divide by 4. N square, 1 by n square, minus 13.6 is the ground state, divided by 4 is the first excited state, second excited state will be divided by 9, right. And everything originates from that spectrum, Balmer lines and this and that. So, people knew about those wavelengths. So, visible light comes when electrons falls from some level to n equal to 2. n equal to 3 to 2 is the most intense and most common light in horizontal spectrum. So, it is all in electron volts. So, the photon which will come out will also be in electron volts. Visible light will be in electron volt, 2-3 electron volts type, correct. So, from mega electron volts which is created at the core during this fusion, it has to come out with as electron volts, and there is a big process involved. These photons are absorbed by that plasma, and this plasma re-emits a photon of smaller energy, and that is again absorbed, and then it again emits, then it is again absorbed. So, there are many sequences, and time is consumed in this process. If the plasma has absorbed the photon, it sets itself into some kind of oscillation or something, right. Whenever it finds that, okay, enough, I have enjoyed this photon long enough, let me emit. So, it will emit. So, long time is taken in this process, absorption, and then it just enjoys that photon, and after some time it emits. So, it takes about 100,000 years to reach there. Yeah. Sun is a collection of hydrogen and gas. How do we see a sharp circular boundary in the sky? It is all gas, it is not moon. Moon has a solid surface, right. So, if there is solid surface, yes, I know here is the boundary, but if it is gas and no container, there is a gas and no container, how come I see the boundary? Yeah.
Other side of the sun means plasma state, then we can consider it as a surface tension, and that's why
Yeah, it's spherical, that is okay. If there is no boundary, and if this mass of gas is there, right, is there, whatever attraction, whatever, is not diffusing, is there, it has to take a spherical shape because of symmetry, that is fine. But when is the boundary, I see a very sharp line. How come I see a sharp line? Why I see sun up to this point and then nothing? There is a fixed angle made by the diameter of the sun on my telescope. So, the gas density cannot suddenly become 0 or very small. If it is gas, it has to diffuse, and okay, there is attraction, all those things are there. So, it does not leak out, but anyway the density will gradually decrease. Okay, good answer. Now, although there is diffusion say across 100 kilometers or 1000 kilometers, but I am looking from a very long distance, and therefore, that 1000 kilometers looks like a small line, right. Okay, good answer. The other will be, yeah, okay.
again, just the surface property, the surface of the sun is not the same, it's not a uniform gas, and so the surface behaves differently and is actually much hotter, and if it contains
right. It is not only density gradient, it is also temperature gradient, and the temperature decides whether the visible light will be emitted or not. Okay. The temperature decides the wavelength, mean wavelength lambda m, which will be emitted. Higher the temperature, higher will be this frequency or energy of photon. Lower the temperature, lower the frequency, longer the wavelength. So, there is a temperature gradient. So, up to some distance, visible light is being emitted. After that, the gas is there, the density gradient is there. It is not boundary of the physical boundary of the gas, but the gas is cold. too cold to emit visible light. It can still emit infrared or far infrared and all that, but that I do not see. Okay. So, that also contributes. Yes.
So when I read something which is called also the coronal heating problem.
Those things we will have perhaps a lecture on the properties of sun. Wave goes on the surface of water in a lake. Is the displacement of water particles vertical, horizontal, or some other? Displacement, yeah, I am talking of displacement of water particles. A wave is going on the surface of the water, the surface is horizontal. So, the wave is spreading like circular wave is spreading on the surface. So, the vibrations of the particles, water particles, they are vertical or they are horizontal or they are something else. Vertical, disturbance is both horizontal and vertical. So, that means the particle has a component in vertical direction. Okay. The displacement of the particle has a component in vertical direction, a component in horizontal direction also. Okay. The wave is spreading, circular waves spreading on the surface of water. So, what is the direction of the displacement of water particles? Vertical, 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 both vertical and horizontal, vertical, vertical, vertical. Now, my problem is if it is vertical, if this particle goes up, what happens to the space which is created there? Suppose we have a water particle and that particle has gone up. So, what happens to the space which is created there? Will there be a vacuum? And if water particle comes down, there is no space there, it is all water, and this water particle at the top, it wants to come down. So, there is no space, how can it come down? If it comes down, it has to push the water, make a space for itself, and when it has to push it in horizontal direction, it will to, because all through there is water, water, water up to the bottom. Okay. So, it has to go this way. Similarly, if it goes up, water from the side will fill that space. Okay. So, water particles will have all motions, something going up down also, but something coming and going in horizontal direction. Some of the particles are going this way, some of the particles are going this way, and so on. So, it is not a purely transverse wave. Okay. The water wave is not purely transverse wave. Yes. हाँ अंदर मिलाओ उनको 10:35 से उनका क्लास है. Milk is heated to its boiling point, it suddenly starts expanding. That's okay. Uphan आना जिसको कहते हैं. The question is, when the stove is switched off, the milk level very quickly comes down. Her question was, she was puzzled that it should take some time to cool down. The temperature is still there, but the moment you switch this stove off, its expansion stops and then it comes down quickly. So, why this sudden coming down when the cooling is not sudden? That was the question. Okay, why it expands once that boiling temperature is attained? Starts to evaporate, not evaporate, evaporation is start to boil. Evaporation and boiling are different. Evaporation takes place at all temperatures, right. So, it starts boiling, but when water boils, you do not see it coming up, but when milk boils, it comes up, unless you break that skimmy thing. Okay, go ahead.
It's because the initial expansion is because the water in the milk is expanding, and as it's heating to boiling point, and the boiling point of milk is of course above the boiling point of water. So by the time it reaches the boiling point of milk, the water is already heated quite a bit. And then I think when you stop, when you reach that boiling point of milk, you go past the boiling point of water, so a lot of the water escapes as steam, and that takes a significant chunk of volume.
Okay, so at that temperature, why it is coming up? Of course, you have covered by that malai thing, right, skimmy thing. So when it reaches that boiling point, then that liquid becomes gaseous state, steam, milk steam if you wish, we can use the word. Now that sudden expansion is because of that sudden onset of this boiling and conversion of this liquid into gas. Because once liquid becomes gas, the volume expands largely. Okay. So that sudden expansion is because of conversion from liquid phase to gas phase, and that needs latent heat. So although the temperature is still the same, once you switch off the stove, you are not supplying that latent heat, and therefore this conversion is suddenly checked. Suddenly it is blocked, no more conversion, because I am not supplying, although the temperature is still there. That girl was very right, it was a question by class 6 girl. Her argument was perfect, that of course it has attained that high temperature and will take some time, few seconds at least, to somewhat cool down. So even then suddenly it stops going up, and then after that it gradually comes down. This sudden stopping of going up is because you have stopped the latent heat supply. Okay, that is the answer to it. All right, so we will stop here.